Hello everyone. In these next couple of videos, we're going to wrap up our trigonometry series with two important laws known as the law of sines and the law of cosines. We've done much work with solving right triangles. Now we would like to take a look at what we need to do with triangles which are not right and how we can go about solving those triangles. We'll start with the law of sines in this video. The first thing we need to understand is an oblique triangle is any triangle that is not a right triangle. And we also need to understand what solving a triangle means. As we did in the case of right triangle, it has the exact same meaning, and it means finding the measure of all three sides and all three angles. An oblique triangle can be solved if we know the measure of one side and any two other parts. Now, these two other parts can be two sides, the other two sides can be two angles, or they can be one side and one angle. But always remember, it's not enough to know the measures of any three parts, because you cannot solve a triangle if all you know is the measure of the three angles. You must have one side to be able to solve any triangle. And by that we mean at least one side. It is impossible to solve a triangle knowing only angles. Always remember that. The types of triangles that we can solve fall into a few categories. It all depends on what measurements we know. If we know the measure of one side and two angles, we have either the Ssa case, that means two angles and a side between them, or the Aas angle, where you have two angles and the side is not between them. Both of these are solvable situations, and we can solve both of those cases using the law of sines. Then we have the case of Ssa, where we have two sides and an angle that is not between those two sides. This is what's called the ambiguous case, because with these you may end up with no triangle, one triangle, or two triangles that are possible. So for these, which we'll discuss in detail at the end of this video, it'll be very helpful to find the height of the triangle. Then we can tell which one of these situations are going to emerge. The next case is SSS. That's when we know all three sides of the triangle. And for these, we will need the next law, which we'll study in the next video, which is the law of cosines first. Then we can use the law of sines, which we learned in this video, to finish it off. And the exact same situation is for SAS. That's when we know two sides and the angle between them. For those, we're also going to need the law of cosines first, which we'll learn again in the next video. And then we'll use the law of sines to finish it off. All right, let's go ahead and formally introduce the law of sines. Basically, in any triangle ABC with sides opposite the three angles having corresponding lowercase lengths, in other words, this is the standard way of naming a triangle. If the angles are capital A, capital B, and capital C, we use lowercase a as the side opposite angle A. We use lowercase b as the side opposite angle B, and we use lowercase c as the side that is opposite angle C. Very logical and simple. If that's the case, then as it turns out, sine of the angle A divided by the side opposite angle A, which is lowercase a, is going to be the same as the sine of angle B divided by B, and which is also going to be equal to the sine of angle C divided by the length of the side opposite the angle C. It's a very beautiful law, and we will prove it to make it a complete presentation. So Notice that we have two possibilities. This is an acute oblique triangle ABC, and on this side we're showing the obtuse case where one of the angles is more than 90. Of course, in an acute triangle, all angles are going to measure less than 90 degrees. And in both of them, if you look at triangle ABD, notice we drop an altitude called the length h in both cases. Of course, in the obtuse case, the altitude from A is going to fall outside the triangle. As you know, we need to extend the side BC in order to see the height of the triangle if A is the vertex we're dropping the altitude from. But in both of the triangles, if you look at triangle ABD, we notice that the sine of B will be the opposite over hypotenuse, so h over c, correct? Notice the same goes on here. We're looking at this triangle ABD now, but the sine of B is still going to be h over c. And the sine of the angle C, if you notice, is going to be h, because we're looking at a right triangle now inside, right? That's why we can talk about sine and cosine. So it's going to be h over this hypotenuse, which is going to be b. So, and that again holds for both triangles. So if we take these two equations and solve both of them for h, we end up with h equals c times sine of b from here. Imagine a 1 under there and cross multiply. And we get h equals b times sine c from this equation. Now, if we take both sides of this equation and divide it by bc, we get the c's canceling here and the b's canceling here, so we end up with sine b over b equals sine c over c. Now, if we had dropped altitudes from B or C, we would have gotten the exact same results, and we would have come up with this version of that equation. So given that both sine C over C and sine A over A are equal to sine B over B, that means they're all equal to each other, and we have proven the law of sines. So it's a very nice, simple proof, but it's extremely important, and we'll be utilizing it from this point forward. For our first example, we're going to look at an Ssa case. So we're going to have basically two angles and a side that is not between them. As you can see, we have angle C and angle B, and the side between them would have been A, but we don't have that. We have side C. So that's why it's called SAA. So let's go ahead and mark the picture with the information that we have. So we have 32 degrees here, 82 degrees here, and we know that the side opposite angle C is 43 feet, so that would be lowercase c. Here we have A, and here would be B. So basically we need to find angle A, side A, lowercase a, and side B of length B in order to solve this triangle. So obviously the easiest place to start would be to go ahead and find the missing angle, since we know two angles and we know that all three angles add up to 180. That'll be the easiest way to fly. So we know that 32 degrees plus 82 degrees plus A should equal to 180 degrees. So A will be 180 degrees minus 32 degrees minus 82 degrees. So we can go ahead and quickly utilize a calculator for that. And we have 180 minus 32 minus 82, and we get 66 degrees for A. All right, so now that we have that, we can go ahead and start applying the law of sines. So we know that, for example, sine C over C is equal to sine B over B. Always write your general formula or equation first, then plug in for minimizing the chances of making any kind of error. So sine of C will be sine of 32 degrees divided by C, which is 43. And for sine of B, we'll have sine of 82 degrees divided by B, which is, of course, unknown. So here we can quickly cross multiply, and we get B sine of 32 degrees equals 43 sine of 82 degrees. So B will be 43 sine of 82 degrees divided by sine of 32 degrees. We'll go ahead and utilize a calculator for that. So the first thing you want to do, make sure that you're in a degree mode. So let's go ahead and check that. As we can see, we're in radian mode, so we need to change that to degrees. Most calculators usually are in radian mode as their default mode, so make sure you check that, and then we can go ahead and exit out of that. So now we can go ahead. So it's a good practice to go ahead and contain your numerator in parentheses. So 43 sine 82, and we go ahead and exit out of both of those parentheses, and then we divide by sine of 32. So we get approximately 80.4 for B, and that of course is going to be in feet as well. All right, so the only thing we have left is A that we need to find. So for that, we can just go ahead and use the law of sines again. We have choices now, but we'll just stick with C. That'll be the least amount of rounding involved. So we'll just use sine C over C again, since we know both of those values. And we'll go ahead and say that's equal to, this time we'll say sine of A over A. So sine 32 degrees over 43 is equal to sine of 66 degrees over A. Once again, we'll go ahead and cross multiply, so we get A sine of 32 degrees equals 43 sine of 66 degrees. So now we get A equals 43 sine of 66 degrees divided by sine of 32 degrees. So we'll go ahead and utilize our calculator one more time to obtain the answer. And so again, I'll go ahead and start with parentheses. I'll put the entire numerator inside the set of parentheses. 43 sine of 66. I'll go ahead and exit out of that. And then we'll divide that by sine of 32. So we get approximately 74.1. And that'll be in feet as well. So we have now basically solved for everything. So there's we have angle A here. This is B, approximately. So, and C was of course given, and so was capital C and capital B, the angles. All right, so the triangle is now completely solved. We did that using the law of sines. Make sure that you can handle a simple situation like this before we proceed. In our next example, we're going to look at an Ssa case. So that means we're going to have two angles and the side between them. Oftentimes, these are presented in the form of a word problem, which is solving some kind of a real life situation. So in this case, Jill wishes to measure the distance across this river. She has determined that angle B is 115 degrees, angle A is 35 degrees, and this length here, C, is 350 feet. So we want to explain to Jill how to find the distance across the river. So we are going to go ahead and utilize the law of sines again. Since we're given C, we're obviously going to want to get angle C involved. So that's the first thing we'll do. We'll go ahead and find the measure of angle C, which is simple because, as we know, it's just going to be 180 minus 180 degrees minus 115 degrees minus 35 degrees. So if we do a quick calculation on that, we have, let me clear that. So we want 180 minus 115 minus 35. So we get 30. All right, so we have this missing angle here now. So now we can go ahead and set up the law of sines. So we know that sine of A over precisely the distance that we're interested in, because we're trying to find this distance across the river. And of course, that's opposite angle A, so we use the lowercase a for it. So sine of A over A equals, and of course the two we want to get involved are these two because we know their values. So sine C over C. So A we know is 35 degrees, so sine 35 degrees over A, the unknown, equals sine of C, which is sine of 30 degrees, over C, which we know is 350. So again, quickly cross multiply here, so we get A sine 30 degrees equals 350 sine 35 degrees. So A equals 350 sine 35 degrees over sine 30 degrees. And now we can get a quick estimate for that. So we'll bring in our calculator again, and we get 300. So we'll go ahead and parenthesize 350 sine 35 divided by sine 30. So the distance across that river is approximately 410.5 feet. Always have units for your final answer if it's relevant to have one. All right, so a very simple, quick application. Make sure you can handle it. All right, so here we have another application. This one is also an Ssa example. And we basically have two lighthouses that are on an east-west line, and they're 200 kilometers apart. And we know that there's a large high-rise located basically at 40 degrees north, 40 degrees east. So that means you have to imagine a north-south line and then go 40 degrees east from that. And relative to this one, it's at north 20 degrees east. So again, you draw a north-south line at that point and then 20 degrees eastward. So we want to know how far the high rise is from the western lighthouse, so this one. So let's go ahead and label our graph here that we have. Let's go ahead and call this point A. And in fact, since we don't want any confusion as to which angle is A, let's go ahead and write it inside the triangle. So let's say this is angle A. Let's say that's B. There's no confusion up there, so we can just call that C on the outside. And notice that here we have a scenario where that's the 20-degree angle right there. So that's kind of hidden behind this picture. So you add that to the 90 that would be right there, and that's where the 110 comes. So inside the triangle that we create here, that internal angle is going to be 110 degrees. Let me get rid of that so that doesn't confuse us. Okay, so basically we know two of the angles, right? So of course a quick thing would be to find angle C, because we know that C is going to be 180 degrees minus 50 degrees minus 110 degrees. So this is simple enough. We can do this in our heads. That's 160 taken away from 180, so 20 degrees. That's what we have here. Okay, so if we complete the labeling, we can see that this will be B and this will be A. Now, we have the capability of finding both, but really what we care about here is B, because that's the distance from the high rise to the western tower. So we'll go ahead and get that involved in our law of sines. So we have sine of B over B equals, obviously we're going to want a pair both of whose values we know, and as you can see that will be C and sine of C. So we'll have sine of C over C. So sine of B is going to become sine of 110 degrees over B, the unknown we're looking for, equals sine of C, which is 20 degrees. Let me make sure that's clear. Okay, well, not really. Here we go. All right, so sine of 20 degrees over C, which, as you know, this is the side C, so 200 kilometers. All right, so now we go ahead and cross multiply. So okay, this screen is annoying. Here we go. Let's try it again. B sine 20 degrees equals 200 sine 110 degrees. So we get B is equal to 200 sine 110 degrees over sine of 20 degrees. So now we're ready to go ahead and do some calculation. We'll bring back the calculator. Let's go ahead and clear it. So we want 200 times sine of 110. Some calculators assume the multiplication. This one does not, but it's a really nice calculator, so I'll put up with that. Divided by, in most calculators, you can just, you know, of this level of sophistication, you can just put 200 sine 110. But with HP, they decided to force you to do the multiplication. This is just updated, so I have to check. Maybe they fixed that. Sine of 20. All right. So we get approximately 549.5 and of course remember here we're dealing with kilometers. All right, so that's how far the western lighthouse is from the high rise that is being observed there. All right, so again, very simple, but you have to make sure that you are comfortable with it. All right, one very nice and quick application of the law of sines is giving us the ability to find the area of a triangle if we have two sides and the angle between them. And the reason for that is if you observe either one of those graphs, what analysis we do here applies to both the acute and the obtuse cases. And notice that sine of the angle B will be H over C. These are the same graphs we saw in the beginning when we proved the law of sines. And also recall that the area of both of the triangles is given by 1/2 of base times height. So notice, for example, in this case, the base is A and the height is H. So we get 1/2 of A times H. But if you recall, sine of b is h over c, so if we quickly cross multiply and solve for h, we get h equals c sine b. So we can get the area by multiplying 1/2 by a by c and by sine of b, which is really nice because look, what we're saying is you can get the area by multiplying two sides that are given times 1/2 times the sine of the angle that is between those two sides. Now, if we had started with another angle, we would have been able to accomplish the same thing for each of the three angles and the sides that surround them. So basically, the one we derived here is 1/2 AC sine B, but you could easily have gotten 1/2 of A times B times sine of C, or 1/2 of B times C times sine of the angle between them, which is A. So we did this. Highly recommended that you do those for yourself. In any mathematical analysis, usually people aren't going to do an overkill and show every possible scenario. They'll usually prove one and have the reader or the observer do the rest, which is great for your own practice as well. So make sure that you know you can try this and establish these for yourself. But a very, very handy area formula if we know two sides and the angle between them. Let's see if we can apply that real quickly. All right, so here indeed we are given two sides and the angle between them. The way that we will utilize this formula is we'll just say A equals 1/2, assuming we can just call those A and C. So 1/2 of 201 times 332. Of course, those are going to be feet and feet, so you end up getting square feet, as you should, as you expect to get for area. And we're going to multiply that by sine of the angle between them, which is 50 degrees. So if we work that out, we get a nice approximate value for the area of this triangle. So instead of 1/2, you could put 0.5. It's much more efficient like that. So we'll just go times 200. Okay, I've forgot that our calculator is a little sensitive. All right, so times 201, and then times 332. We don't even need parentheses since it's making us do the multiplication anyway. And then we'll go times sine of 50. So take a few seconds just to make sure you put the right numbers in correctly, and go ahead and hit enter, and you'll have the area. So the area of this triangular plot of land is approximately 25,000. Let's just go to a whole number, 25,560 square feet. All right, so a very nice quick application of the law of sines, enabling you to find the area of any triangle as long as you know two sides and the angle between those two sides. All right, next we're going to look at the Ssa case. This is called the indeterminate case because the number of triangles that are possible varies. Sometimes if the third side ends up being too short, you end up with no triangle. Sometimes you end up with exactly one triangle. That's when the third side actually happens to be the same as the altitude's length, which is called height. If the third side is sufficiently long, you're going to have just one triangle possible. And sometimes the third side falls somewhere between this side and the altitude, in which case you can drop one side in this way and one that way, so you get two possible triangles. Notice you get ACB1 or ACB2. So it's going to be really important for us to find the height to determine how many triangles we're going to have. Some textbooks and instructors don't push that too much, but it's extremely useful to have the value of the height, as you can see, because then you can determine whether you're going to have no triangle, one triangle, or two triangles. A few of the things that you need to really understand before we proceed and successfully handle these is that for any triangle, an angle inside that triangle is going to have sine values between 0 and 1, but of course not 0, because we're dealing with actual positive lengths, and possibly 1. Now, if it is 1, of course, the angle is going to be 90 degrees and you have a right triangle, so there's no need for these laws. We already know how to solve right triangles. Supplementary angles have the same sine value. That means the sine of an angle and the sine of its supplement are the same. If you look at the unit circle, you'll understand this very clearly. Now, as long as a triangle has sides that have different sizes, obviously, the smallest angle is always going to be opposite the shortest side. The largest is going to be opposite the longest side, and the middle size one, of course, is going to be opposite the middle size, the length side. Now, as long as, of course, the sides have different sizes. Otherwise, two of them may be the same, etc. For the indeterminate Ssa cases, it's, as I said a minute ago, it's extremely helpful to find the height before you proceed with the rest of the problem. All right, so here's an SSA example. We're going to solve the triangle given that A is 55, lowercase a is 23, and B is 25 meters. And basically, since it's an ambiguous case, it's very good to go ahead and do a quick plot. So we'll just draw a triangle to the best of our abilities. So we have, if we go ahead and call this angle A, we know that this is 55 degrees, and B is going to be somewhere around here. So we know that the side B, which is opposite angle B, is going to be 25 meters. And we have the side opposite angle A, but we're not exactly sure where that's going to hit. So we don't know if it's going to go straight down, be a right triangle like this, this one, or whether it's going to be long enough to just go once like this and give us one triangle, or whether it's just long enough so that we can go this way and get one triangle and go the other way and get another possible triangle. So we have to find out. So the best thing we can do is go ahead and find the height first, as I've been recommending. So because then once we have the height, we can use our guidelines here to determine how many triangles we get. So We'll go ahead and label that h. So we know that sine of 55 is h over 25 in this triangle. So if we solve that for h, we get h is equal to 25 sine of 55. So let's go ahead and calculate that. Again, you want to make sure you're in degree mode, but we've already done that, so we don't need to, but generally speaking, you should always make sure. So we want 22 times sine of 55. So we get 18 approximately. So let's just say approximately 18. So notice that the value of a falls exactly between h and b. Let me say that more clearly. Notice 23 falls between 18 and 25. If you recall, this is h, the 23 is a, and the 25 is b. So that tells you we're in this category here. That's the one case where the value of a is exactly long enough so that it can sweep this way once and give us this triangle, or it can go that way and give us that triangle. So we know we're going to have a case of two triangles. So now we'll go ahead and proceed with that in mind. So as far as solving it, we know that sine a, we're going to go ahead and apply the law of sines. So sine a over a equals sine b over b. So for sine a, we're just going to put sine of 55 degrees over a, which we don't know how much it is. It's a 23. And that's going to be the same as sine b over b. We do have the value of b here. B is 25. All right, so we go ahead and cross multiply and solve for sine b. So we get 23 sine b is equal to 25 sine of 55 degrees. So sine b is going to be 25 sine of 55 degrees over 23. So we're going to go ahead and plug that into our calculator, and we're going to need to because remember, b will be the inverse sine of ditto, right? Meaning the inverse sine of all that. So we're going to go ahead and invoke. Again, make sure you're in degree mode, otherwise this will be completely nonsense answers. All right, so we're going to do the inverse sine of, all right, we'll go ahead and open a new set of parentheses to contain the numerator into, so 25 sine of 55, and then now we'll exit those two and divide it by 23, and that's what we end up with. So 62.9, so approximately 62.9. But remember, supplementary angles have the same sign values, so we're going to say or B is approximately 180 degrees. Oh, by the way, let's not forget the degrees, because otherwise it'll be interpreted as radians. 180 degrees minus 62.9 degrees. So let's go ahead and bring our friend back. So we have 180 minus 62.9, 117.1 degrees. So okay. So notice we can kind of do a quick sketch now. So we have two possibilities. One is when A doesn't change, right? And this length here doesn't change, the length of B. That's still going to be 25 meters, right? But notice now you can have one case where the angle B here is 62.9 degrees. Which will look something like that. And the other case where the angle B is going to be quite larger. So this time we're going to go like this. So this piece is not going to be there. It's just going to go like that. So here our angle B is 117.1 degrees. And here we have C in both graphs. All right, so at this point, we're going to be solving two different triangles, right? And that's going to be easy now. So what we can do is label these slightly differently. We can call this one, we can call this one B1 and call this one B2. So if you're going to go with that terminology, let's call this one C1 and C2. So here we'll have C1 and C2, and A, of course, the value of A, which is 23 meters, is not going to change. It's just that one time the 23 went this way, in the other case the 23 came this way, but it's still the 23. All right, so now looking at this triangle, right, we end up with A over sine A equals, for example, we can handle the C's. Notice that we can find the capital angle C1 very quickly. We're just going to do 180 minus 55 minus 62.9. So we get 62.1 degrees here. While we're at it, let's go ahead and take care of the other one too, this C2 here. So 180 minus, don't forget the A here is the same as well. So minus 55 minus this time 117.1. So 7.9 degrees, much smaller angle. All right, so we're going to be handling this one first, the C1. So we get is equal to C1. Oh, by the way, notice instead of writing the sine A over A, you could also start with A over sine A, B over sine B. That's what I was doing here. So, but I shouldn't have used the capital letter. So let me just erase that and go back to our original. So let's just go with sine A over lowercase a equals sine C1 over C1. Okay, so sine of 55 degrees over 23 is equal to sine of 62.1 degrees over lowercase c1. So when we cross multiply, we get c1 sine of 55 degrees equals 23 sine of 62.1 degrees. So C1 will be 23 sine of 62.1 degrees divided by sine of 55 degrees. All right, so we go ahead and compute that to get our approximate value for C1, and then we'll be basically finished with the left triangle. So so we're going to do 23 times sine of 62.1, and we'll go ahead and exit that and then divide by sine of 55. So we get 24.8 approximately. So in this first scenario, this is approximately 24.8 meters. All right, so the last thing we're going to do is we're going to go ahead and let me get some space here by doing a little trick here. Okay, so let me go ahead and fuse it so it doesn't keep bugging us. All right, so now we're going to go ahead and take care of this other one, find C2, and we'll be basically done. So this time we're going to use the same. It's going to look very much like this, except we're going to have C2 and C2. All right, so sine A over A equals sine C2 over C2, and we plug in now, so sine of 55 degrees over 23 equals sine of 7.9 degrees this time over C2. Clearly we expect this value to be less than the 24.8 we found. Make sure that decimal is there. I didn't write clearly, but that's 24.8 meters. We expect C2 to be less than that. So if that doesn't turn out, that means we made a calculation error somewhere. All right, so here we'll cross multiply again, so we get C2 sine of 55 equals 23 sine of 7.9 degrees. So we get C2 is equal to 23 sine of 7.9 degrees divided by sine of 55 degrees. And we go ahead and calculate that. Actually, we didn't want that. We wanted this. Okay. So, all right. Notice how close that's going to be to this expression. So I'm going to cheat here and copy that. And then I'm just going to go ahead and change the 62.1 to 7.9 because everything else is the same. And we get 3.9 approximately. So approximately 3.9, which satisfies our thinking, because this should have been, this triangle here is actually exaggerated. This angle is much more than 7.9 degrees. So if this were drawn to scale, you would have seen this would have been much shorter. Okay, so 3.9 meters. So C1 24.8 meters, C2 3.9 meters. All right, and those are our two possible cases. So that's why these SSA type are called ambiguous, because you get different possibilities. All right, so the first one that we looked at was the case where two possible triangles exist. And again, if you calculate H, you'll know that from the get-go. That's why I strongly urge you to calculate H first. That way you'll know where you're headed. Let's look at another one. All right, so this time we have another SSA example, and if we take a look at a sketch, we notice that we have A is around 44 degrees, and we have C is 7 feet. So notice that if you have the triangle looking like this, then we can have the C either at this vertex or at that vertex. Since I'm given the side opposite the angle C being 7, rather than putting C up here this time, we'll put it down here, so that then this will be the side opposite C at 7 feet. So that means our B will be somewhere up here. All right, so as recommended, we'll go ahead and try to compute the height now. So we have sine of 44 degrees equals H over 7. So h equals 7 sine of 44 degrees, which is approximately, let's bring up the calculator. All right, so 7 times sine of 44, so approximately 4.9. Now, notice that the side opposite A is 11. So there's no way it can swing this way, correct? Because this is only 7 itself. So this time there's only going to be one angle possible. So we will see another reason why that's the only possibility in a minute, but just intuitively speaking, you can see this is going to be a one triangle situation. So let's go ahead and use the values that we have to set up the law of sines to see what comes up. So we have sine of A over A equals sine of C over C. Those are the values we have to work with. So sine of A over which is 44, so sine of 44 degrees over A, which is 11, equals sine of C, which is unknown, over C, which is known, and it's 7. So we get 11 sine C equals 7 sine 44 degrees. So we get sine of C is equal to 7 sine 44 degrees over 11. So we get C is actually the inverse sine of ditto being all that. So let's see what that turns out to be. Let's bring up the calculator again. All right, so we start with the inverse sine. Make sure you don't forget that. And we have 7 times sine of 44. Went one too many, divided by 11, and we end up with approximately 26.2 degrees. Now we know that 180 minus that is going to have the same sign. So if you compute that, we get 153.8 degrees. Now, the problem, of course, with 153.8 degrees being opposite angle C, side C, which is 7 feet, would be the fact that side A is larger than side C. So there's no way the angle that's opposite side C can be larger than the opposite that is the angle that is opposite angle side A. So therefore, the only possibility, as we had already determined by looking at the height, is one triangle. You see that? So just to recap, notice C is 7 feet and A is 11 feet. So if we remember, we mentioned earlier that in any triangle, the side opposite the largest angle is the larger side. largest side, and the smallest angle, the smallest side, etc. So being that 11 is more than 7, there's no way the angle opposite 11 is going to be smaller than the angle opposite 7. So this cannot happen. So 153.8 is not going to work. So the only possibility is that C is 26.2 degrees. So the 11, as we mentioned earlier and assumed earlier, can only swing this way. And here is going to be our C at 26.2 degrees. All right, so that only leaves B for us to calculate, which is going to be here, of course. So now we say sine of A over A equals sine of B over B. We need to quickly compute the angle B, which is going to be very easy now, because B is going to be 180 minus 44 minus 26.2. All right, so when we go ahead and compute that, oh, come on, cooperate. All right, so we have 180 minus 44 minus 26.2. We end up with 109.8. So we get 109.8. And now we can go ahead and plug into here. So we have sine 44 degrees over 11 equals sine of 109.8 degrees over B. So B times sine of 44 degrees equals 11 sine of 109.8 degrees. So B will be 11 sine 109.8 divided by sine 44 degrees, which we will now compute. So 11, let's go ahead and clear first. All right, so we'll start with parentheses. 11 times sine of 109.8 and we will divide that by sine of 44. So approximately 14.9. So now we have solved the triangle because we have all the items that we need. Of course, if you have the time and you're doing this properly, you'll want to list everything. So for example, you'll want to say A is 11, A is 44 degrees, B is, of course it's approximation, but we can go ahead and put equals, you know what we mean. B equals 14.9 and capital B is 109.8 degrees. C is lowercase c is 7, and uppercase c is as we discovered earlier 26.2 degrees. And of course those should have feet next to them. I just ran out of space. But if you present your work nicely, where you list all the sides and all the angles, that's always greatly appreciated by anybody requiring your work, whether on the job or in the classroom. So all right, it's always important to present yourself properly, because that's good habits also minimize the chances of making mistakes. There are different reasons why you want to be organized. All right, so that's another good example of the Ssa case. We'll do one more and call it the day. All right, for our last example, we're going to look at another Ssa case, indeterminate case, and we notice that we're given B this time. So when we make our preliminary sketch, we'll go ahead and call this side B, and we're given the side opposite being 9, and we have one of the other sides being 25, so we can put the 25 here, and that means whatever vertex we get on this side will be called A, because we left this one as A equals 25 up here. So let's go ahead and drop an altitude and find the H to test the waters. So we have sine of, this is of course 55 degrees equals H over 25. So we get H equals 25 sine of 55. And when we calculate that, let's go ahead and clear all that. So 25 sine of 55, we get 20.5 approximately. So notice that the side opposite angle B is supposed to be 9. So that means there's no way, because the shortest possible distance between this side, this vertex here, and this side will be 20.5. So there's no way the 9 is going to make it. Okay, so this is the case where there is no possible triangle. And notice how the value of H, which is 20.5, falls exactly between A and B. Okay, 20.5, notice, is exactly between A and B. When this happens, you know, the B and A in this case, the location of those doesn't make any difference. B and A, because B here is a 9, which is, and this is, remember, H. Now, whenever this happens, you're going to get this zero many triangle situation. Now, let's say you were being lazy and you didn't do the H test first, like I've been recommending so heavily. So if, let's say, you just dived right in, you say, hey, I have A's and B's, I'm just going to do the law of sines, right? Let's see what happens if you did that. So you have sine B over B equals sine A over A. So sine of 55 over 9 equals sine of A over 25. So we get 9 sine A equals 25 sine of 55. So sine A equals 25 sine 55 over 9. So A is going to be the inverse sine of ditto. So if we've done this correctly with our analysis earlier, this should be problematic. There should be some kind of error that we get. So let's go ahead and check that. So we have inverse sine of 25 sine of 55 divided by 9. We got the error. And of course we know why. Because if you calculate this, I guarantee you that this will be larger than 1. So let's just copy that, but get rid of the arc sign and just compute that. Notice 2 so we were trying to find the inverse sine of a number larger than 1. So the good news is, even if you are in a lazy mood and you don't test the H, like I've always been, in the past couple of problems really urging you to do, if you don't do the H test to kind of get a feel for how many solutions you're going to have, well, to determine actually, then if you try to keep going, you run into an error in situations where there is no triangle possible. So that's the good news. All right, so on that good news, I will urge you to practice these heavily and be safe until the next time that we meet.